Learning Outcome 2-4. Determine memory, causality, and stability, given an impulse response. We've been introducing in this chapter the idea of impulse response. This is something that exists whenever our system is linear and time invariant, LTI. When our input is an impulse, the output is the impulse response. This impulse response, whether it's discrete time or continuous time, contains lots of information about our system, including the information about whether the system has memory, is causal, or is stable. Those are 3 of our 5 system properties that were introduced in Chapter 1. The other 2, linearity and time invariance, we know are satisfied because we've defined this to be an LTI system. Memory. An LTI system is memoryless if and only if h of t is k delta of t, or h of n is k delta of n. This is the definition for how we can determine whether a system has memory based on the impulse response. Our impulse response is a scaled impulse at time 0, whether it's continuous time or discrete time. This works because as we're doing our convolution and we're flipping our h of t and sliding along our x, we're going to then isolate our x value at a single instance of time to produce every output. And because that impulse is at time 0, when it is sliding along, it's at time t, therefore it's going to produce an output y of t at exactly that same instance of time. So if we were to consider this from the continuous time point of view, y of t is a convolution of x and h. If our h is k times delta of t, the output is going to be kx of t based on the sifting theorem, where the convolution of x with delta of t is x. Therefore, because this has the same time argument as this does, our system is memoryless. You don't need to go through to show this for every problem, but this is the reasoning behind why it works. Let's try some examples. If you are told that h of t is 2 times delta of t, does the system have memory? We can look at that impulse response. It's an impulse at time 0, and it's only at time 0. Everything else is 0. Therefore, according to the definition we just saw, since h of t is a scaled impulse at time 0, the system is memoryless. You need to give some indication of how the definition relates to the impulse response that was provided to you in order to get credit. You can draw a picture and then indicate that this is an impulse only at time 0. You can point to the equation, say this is an impulse only at time 0. Do something to indicate you're referring to the specific problem and not just reciting a definition. Another example. Here h of n is 2 delta of n plus delta of n minus 3. Let's look at that. That does have an impulse at time 0, but it also has another impulse at a different time. Therefore, it does not satisfy the requirement that we only have the impulse at time 0. The answer is that since h of n is not solely a scaled impulse at time 0, which you can indicate by referring to the second impulse in the equation or the second impulse in the picture, then the system has memory. Another way of stating this is to say that the system is not memoryless. We can look at this also from the equations. If we substitute in the h of n that was provided to our convolution, again by the sifting theorem, x of n convolved delta of n is x of n, and x of n convolved delta of n minus 3 is x of n minus 3. Because this input has a time argument that's different than our output time argument, our system has memory. Causality. A discrete time LTI system is causal if and only if the impulse response h of n is 0 for all time n less than 0. A continuous time LTI system is causal if and only if h of t is 0 for all t less than 0. Note that both of these are looking for our impulse response to have 0 value, 0 amplitude, when we're time negative, whether it's discrete time or continuous time. Not causal can also be described by saying that the system is acausal. Let's look at why this is the case. Consider convolution, where we have an x of t and an h of t with certain starting and stopping points. When we flip our h of t in the convolution process, our variables t change to tau, and our time indices for our h change from c and d to t minus d and t minus c. As we slide our h past our x, we're going to get our first non-zero value when t minus c reaches a. This occurs when t is a plus c. If our c, which is our starting point for our impulse response, has a negative value, then the starting time for our output, which is at time a plus c, will have a value smaller than a, which is our starting time for our input x. That means that the output of this convolution will start before the input starts. That defies the rules of causality. Therefore, if c is less than 0, our system cannot be causal. Another example, h of n is 2 delta of n plus 3 delta of n minus 3. Is this causal? Look at time less than 0. When we're time less than 0, do we have any non-zero values? No, all of these are 0. The only non-zero values occur at time 0 and time 3, which are non-negative. Since the h of n is 0 for all values of time n less than 0, then the system is causal. Again, indicate that through the picture or through the equation that we have a whole bunch of 0 values here for all negative time in order to earn your credit. Another example, h of t is 2e to the negative 3t u of t plus 1. Here's what it looks like. Is this system causal? Look at our time prior to 0. Do we have anything that's non-zero there? Yes, there's this huge amount of non-zero amplitude for h of t before time 0. Since the impulse response is non-zero for values of time between t is negative 1 and t 0, then the system is not causal or the system is acausal. Note how this answer refers to the specific question that was provided. Stability. A discrete time LTI system is stable if and only if the impulse response is absolutely summable, which means that the sum of the absolute value of our impulse response is less than infinity. A continuous time LTI system is stable if and only if the impulse response is absolutely integrable. That means that the integral from negative infinity to infinity of the absolute value of h of tau d tau is finite. To get credit for a question on stability based on the impulse response and a homework or an exam, you must determine the value of the sum or the integral and provide that numerical value showing that it either is finite or is not finite. Without having worked out the sum or the integral, you will not get credit. Let's look at an example. h of n is 2 delta of n minus delta of n minus 3. That's what it looks like. Let's figure out what the absolute sum is. We take every value here, take the absolute value, add them up. Is this finite? Yes. Therefore, since the absolute sum of h of n is 3, which is finite, then the system is stable. Another example. h of t is 2 u of t plus 1. Is this system stable? Take the integral of our absolute value. Because it starts at time 1, our limits of integration change from minus infinity to infinity to negative 1 to infinity. Our amplitude is 2. Integrate, and we get 2 times infinity. Since the absolute integral of h of t is infinite, the system is not stable. Note that the system is not stable even though h of t does not go to infinity. H of t is bounded, but whether or not this h of t is bounded is totally irrelevant to this definition. When you're provided with an h of t, you need to calculate a sum or an integral and look and see whether that is infinity or not, and do not look at the amplitudes of your h of t or your h of n. A common problem students have is deciding whether to use the definitions for memory, causality, and stability from Chapter 1 or Chapter 2. If you're provided with an input-output equation, then you use the methods in Chapter 1 from Learning Outcome 1-3 in order to determine memory, causality, and stability. You'll know that it's an input-output equation because they're going to contain the variables x of t and x of n for input, or y of t, y of n for output. If you see x's and y's, it's an input-output equation. Use Chapter 1 definitions. If a system is defined by the impulse response, the methods described here, Learning Outcome 2-4, are the ones that you use to determine your system properties. And you'll know that it's an impulse response if you see the letters h of t or h of n. If you see x's and y's, use Chapter 1 definitions. If you see h's, use Chapter 2 definitions. I hope that helps.